Thank you, Mr. Chairman. Thank you, organizers, and good morning, everybody. So, Element 6 is part of the De Beers group of companies. So we are into diamond and specifically making tools for cutting out of synthetic diamond. We make a range of different products for a range of different industries. You can check us out on the website. This talk, the authors are based in our R&D facility in Oxfordshire in the UK. If any of you guys are ever in town, just drop me a note. We'd love to tour you around. It's one of the things we do in the building. And where I'm originally from, our factory still down south in South Africa, where we make the tools. So diamond, as you know, the hardest known material, etc., but very brittle due to the cleavage planes, of course. And there's a lovely version of a 111 cleavage plane, giving us a very low fracture toughness. So this is no good for an abrasive tool. Of course, it allows us to make wonderful gems and things, but not good for a tool. So we have to go polycrystalline. So this is where we take a lot of single crystal diamond grains and sinter them together. So we're talking true diamond bonding. This is an SEM micrograph. So the black is the diamond grains, and the gray is the liquid phase binder between the grains. It's almost always cobalt based. So what we get at polycrystalline for crack deflection. So that pushes our fracture toughness up. It's still not earth-shattering, but it's good enough fracture toughness for us to now have a tool. So if you have in your mind, then you think about polycrystalline diamond, just think 95% diamond and about 5 volume percent of binder. So here I've got a picture. I've now eaten away the binder, but I've etched away the binder to make it easier to see. So in your mind's eye, you can imagine, well, if that's a grain boundary between the diamond grains, then what we're going to try and do is have a crack deflecting at the grain boundaries. And also, once it goes into the binder pool, this nice soft, squidgy cobalt pool to absorb the crack energy. So that's the toughening of polycrystalline diamond. So now let's go and make a tool with this stuff. So we call, in the industry, we call these cutters. We are rock cutting with our PCD cutters. And it's almost always a polycrystalline diamond table centered on a hard metal substrate. You'll notice that the cobalt from the substrate, that's a very handy source of the cobalt. And just to give you a wee idea, I got one on my key ring here as a demo. That's the sort of the size that we're talking about. Now, when you're working with diamond, sintering diamond, you have to be very high pressures and very high temperatures. So that means that when you bring the material down to room temperature and pressure, you generate significant residual stresses in the product. So we're dealing with big inbuilt residual stress there, up to a gigapascal. Sometimes enough to crack the material itself if we haven't got the sintering quite right. So anyway, the bottom line is that we have wonderful hardness and sufficient fracture toughness to go off and cut rock. So we will make these products, and they're called our Syndrol range, and these are used in the oil and gas drilling industry. So we sell the cutters to drill bit manufacturers. There's the scale with the goggles, you can give it a good hug, and off we go drilling for oil. But of course, a far more exciting future will be cutting rock for geothermal drilling applications, and why not a hole for every home, you know? And here we are in Italy, very proud and rich history of geothermal power. So this is where we want to build the future of our products on, but it's very difficult. Drilling geothermal sites, very, very challenging lithography. So we've got to really improve the durability of our cutters. So that's why I've been sent here to speak to all of you people there. So how would we, or what is durability? If we say, well, we're selling a cutter, so durability is retaining the cutting edge. Simple as that, under the thermomechanical loading of application. So let's have a look. Here's our cutter. This is what we're going to do. We're going to put it on our edge just to rotate ourselves, and we're going to go and cut the rock. And you can see as we move in this direction here, the rock chip flows up here. There's the depth of cut. So you can see that we are hammering our product on the face and the wear. So we're now just, right, let's get to the heart of this. What's the actual challenge here? So we look at, I'll also be showing you real pictures, but schematically it goes down to this here. We are experiencing mechanical overloading on the face, and depending on how close you are to the edge chips get bigger and bigger, and eventually they will peel in, and we'll call those broken tooths. But we're also hammering it from the side. Same sort of pattern, but now we call it a spall going up to the top. So these yellow lines just indicating the approximate track paths for our various events. And what we have here, we have high temperature, high frictional loading here. So we're dealing with temperature as well. So of course, what we're seeing in reality is the combination of these. So we sell a pristine product and it comes back from the field completely smashed, and we have to figure out what's happened. Well, all that's happened is it is a sum of these three forces that we're fighting: abrasion, impact, and thermal. So nice controlled wear, impact, and the thermal. So let's go into the lab now. Let's see what we're going to do. So we're going to do mimicking the field. Here is a lab test. There would be our cutter. We would braze it into the bit just like our customers would, and then we're going to go and cut granite rock. I don't know what the volume is like here, what the volume will be like. So that's our test. If you heard at the very beginning that the rock is hexagonal, so there's impact as well. So we've got abrasion, impact, and thermal. These are brutal tests. And it always boils down to one little number on a graph. When you watch it and you see what our product has to do, it's an incredible material and they're operating under very extreme circumstances. So we start off like that, we get a lovely wear scar forming, and then nothing. And then the boss says, Nilen, what are you doing? Are you still having this problem? Go and sort it out. So I'm giving some more examples now. This would be what we would call a shear or tangential load failure. The cracks coming across, and of course you just have to push that a few more times, and you get this shear failure, what our customers would call broken tooth. So we would obviously want to speak their language. So the opening caveat that I didn't do, fracture mechanics novice here, so I'm giving you problems rather than answers, but that's where we are at the moment. So how do we try and look at these things, a cross section, and have a look at the crack? We go in closer and closer, and we see time and time again that the crack propagation is almost always transgranular. There's very little intergranular, which we suspect we might want to promote. There's an example of a radial crack going in. So a crack going in vertically. What does this guy do if you push him just a little bit further? Off they go. So these are the sort of pictures that the customer will come back to us and say, oh, we bought your cutter and it looks like this. What has happened? We go back and try and break it down into simple schematics and say what's going on. This is the bane of our life, the spalling and the edge chipping there. I think the fracture mechanics experts would recognize these sort of beach marky things. I don't know what the official term is, but we see this all the time. Spalling and edge chipping is a real concern for us. Right, so it boils down to this. And it's almost going from that to that in a matter of however many feet our customer drills is a problem, A, because it gives you suboptimal performance, but it's more, a bigger problem is that it's predictability. The customer would rather be able to get 70% of the performance all the time than record-breaking, terrible record-breaking, etc. So it's the predictability. Having a durable cutter. So let's take that wedge scar, cut through the mid plane there. You can see here, I would tell my boss, everything looks beautiful here. I've just got good abrasion. But when I cut through, I see this crack here. And of course that crack is about to, he's gonna carry on. You got the point. But as we go, we love looking at the micrographs and getting deeper and deeper into the cracks. And that would be a nice example of where we start seeing little cracks in between the diamond grains, things, all sorts of damage building up. We're at the point where we're like, we see the damage, we see it happening here. We know why it's happening. What do we do about it? How are we going to solve this problem? And that's where we come on to, hopefully, some strategies. So, strategies, final section. How are we going to improve it? Well, if we've got 95% diamond, 5% binder, can we maybe get away with having some non-diamond particles in there? You know, maybe we only need 93% diamond, 2%. So the addition of non-diamond grains, not great contrast there. But you can see here, this is a slightly frustrating picture for me when we saw it. The crack going neatly between the two non-diamonds, completely ignoring our track, if you like. We hoped to see crack deflection and bouncing around, etc., etc. And there's another picture. Not quite sure why I included this in the thing, but it's just to give you an overall where there's so many cracks happening here in this brutal environment. Functional grading. Can we take different types of PCD? So when I say different types, I'm talking about different volume content. So remember the 95.5, maybe 96.4, 93.7 will have different cobalt content, therefore different thermoelastic properties. Therefore, we will get crack deflection through the approach of functional grading. These sort of pictures, we make them in the lab and they look great and they look good in a paper and they look good in a patent, but do they change the overall performance of the cutter overall? Still struggling with this. Looks good on paper, hard to make it count in real life. Here's another example where we've got a tougher grade of the diamond, and you can see it's keeping the damage nicely contained, targeting the predictability of the thing. We talked about thermal. Thermal is important. That cobalt, when it heats up, it does bad stuff. It graphitizes our diamond, all sorts of things. So let's talk about alternative binder metallurgies. This is a cobalt PCD after 800 degrees, all sorts of binder extrusion, pushing out on the diamond grains, cracking them, all sorts. Same thing with a cobalt rhenium, a more thermally stable binder. Beautiful. This is the picture when you put these two together. The customer buys your product. Oh, right, we'll have one. We'll have some. This I thought was a nice thing for the crack parts community. We seem to be getting in-grain crack deflection. So this would be one diamond grain. Excuse the poor quality of the micro graph, but that's about 70-degree crack deflection as we go, which is the angle between 2,111 each like more better if that would be exactly 70, but never mind. So to wrap it up, conclusions. Polycrystalline diamond is a wonderful material for doing all sorts of abrasive applications because of its hardness, and it has sufficient fracture. So it's this. We want to turn the sufficient into excellent. Then we're a far away, and we need to do that because geothermal applications, which we believe are the future for us, are demanding it. But that means that we need strategies for handling our crack paths. And so far, we're talking about residual stress management. I didn't go into the details of that, but it's an obvious thing. Alternative binder metallurgies and the various crack deflection strategies that I showed you within. Thanks. So I don't know how the time is going, but thank you for listening.